In the last video, we learned about the directional derivative. And at the end of the video, I said we were going to learn about a particular type of directional derivative called the gradient. So if I can draw here. Let's see what the gradient is. So let's recall the definition of the directional derivative. So we're looking at the directional derivative in the direction u of the function f of x, y. And we learned that this was we learned that this was f sub x of xy cosine theta plus f sub y xy sine theta. Okay, and you may notice that we could actually write this as a dot product. This is a dot product of the vectors f sub x, f sub y with cosine theta, sine theta. And we're interested in this vector that's composed of partial derivatives, where in the x component, it's the x partial derivative, and in the y component, it's the y partial derivative. We have a special notation for this, and it's said grad f. So it's an upside down triangle here. We say this is grad f dot cosine theta sine theta. So the upside down triangle, so here's some notation. Upside down triangle, it's called a nabla, N-A-B-L-A, but it's usually read as grad. So the upside down triangle, it's like a capital delta upside down, is a nabla, but we reread it as grad. So this would read grad f, right? Or the gradient of f dot cosine theta sine theta. And so that's our definition. So if we have z, which is f of x, y, we'll let this just be a function with partial derivatives that exist, then the gradient of f is, and again, it's grad f, or nabla f, of xy, and it's defined to be the vector f sub x, f sub y. Right, and then if in 3 variables, maybe I'll just write it like shorthand notation, you'd say grad f is equal to, so if we had w equals f of x, y, z, say, then grad f would be the vector, the 3-dimensional vector with components f sub x, f sub y, f sub z. And the gradient is very important in application, as we'll see in a little bit. But first, let's just understand how to calculate the gradient. And we understand how to calculate the gradient since we understand how to calculate partial derivatives. So let's just do one example here really quickly. Oops. So let's do an example. Let's let f of xy be sine 3x cosine 3y. And then let's find the gradient of f. Well, the gradient of f is the vector given by f sub x, f sub y, which is, if we take the partial derivative with respect to x of f, well, that's going to be 3 cosine 3x times cosine 3y. And then we need to take the partial derivative with respect to y. And if we take the partial derivative with respect to y, we'll get negative 3 sine 3x sine 3y. So my gradient, my right angle bracket's going off the screen there a little bit. Okay, and so this is kind of at the very at the most basic level, calculating the gradient just boils down to calculating partial derivatives and then plugging them into the proper components of the vector. And so let's see some properties of the gradient. Here's a handful of properties. So again, let's just consider z equals f of x, y, and let's assume that it's differentiable. Okay, so the first property is if the gradient is 0, so I'll say it's the 0 vector, right? Then the directional derivatives of the function are 0 for all directions, right? So for all u equals cosine theta, sine theta, right? Because think about what the definition or how we could express the directional derivative here. We could express it as the gradient dot our unit vector cosine theta, sine theta, right? But if the gradient is 0, well, then it's going to be 0 dot something. So the whole expression is going to be 0, right? Okay, so the next property we have is if the gradient at a given point is non-zero, then the directional derivative of f at the point x naught, y naught is maximized when u points in the same direction as the gradient. So I'll just say as the gradient, and the maximum value of the directional derivative as points vary is the magnitude of the gradient at the point x naught, y naught. Okay, and so we'll want to think about what this is saying. There's an analogous statement with a minimum. So I'll state that, and then we'll kind of talk about what this means, maybe a little more intuitively. So the third property I'd like to talk about is that the directional derivative is minimized when u points, that looks like a W, u points in the direction of minus the gradient. So the negative gradient, right? So which is the gradient just in the opposite direction, like by rotation of pi. And the minimum value is the magnitude of negative the gradient at the point. Okay, and so again, number one, this first property here was saying that if the gradient's 0, then all directional derivatives are 0 at that point, right? So I'm kind of here, what I should be saying is, you know, it's the gradient at a point. And instead of a, b, let me use f of x, y, or x naught, y naught. Right, it's saying if you're at some point and the partial derivatives aren't changing at all, well, then your function's not changing at all in any direction. That's what the first one's saying. The second and third ones are saying that the maximum change in your surface, so 2 here is saying the maximum change in your surface is always in the direction of the gradient. And so that's like noteworthy here. So here's a note. the most rapid increase of a function is in the direction of the gradient, which again is the vector with components that are the partial derivatives. So if you'd like to think, let's imagine we have, like, there's some mountain here, say, and there's a river running down the mountain. Let's say it kind of winds a little bit like this. So here's some little like stream or river running down the side of a mountain, and you could express flow rates along this river. And if you pick a point in the middle of this river, say you're a little frog right in the middle of this river, and or say a leaf, even better. So if this is a leaf kind of flowing along this stream, it's going to flow along the path of least resistance. And the path of least resistance is also going to be where this is, where the water is flowing the fastest. And the direction that the water is going to be flowing the fastest is the gradient of the flow represented as a function in two variables. So this leaf is going to tend to follow wherever the water is most rapidly increasing, right? And that direction is the gradient. And so the gradient gives us the direction of the most rapid increase of our function. And because the direction of the gradient gives us the most rapid increase, well, then it's clear that negative the gradient is going to give us the most rapid decrease because it's increasing in the opposite direction, right? And so this is kind of some intuition here as to what the gradient is measuring kind of realistically, right? Because just as a definition, we know it's just a vector of partial derivatives. But what it's actually measuring is the direction of maximum increase. And so this is important in a plethora of applications, right? Because maximizing increase, well, like profit for one, right? There are many places where attaining a maximum increase is what you want. So, okay, there's one more theorem I'd like to quickly state, and then I'd like to do one example, and then from there we can start a different application of partial derivatives, and it's finding maxima and minima of surfaces. But for now, I want to state one more theorem about the gradient, do an example, and then that'll wrap up this video. So first, let's let z equal f of xy. Let's let this be a function with continuous. So let z be a function such that we have continuous first order partials. In a neighborhood, let's say U containing the point x naught, y naught, right? Well, then the gradient at x naught, y naught is normal, meaning like orthogonal to the level curve at x naught, y naught. And so what is this theorem saying? Well, let's imagine our surface is a sphere. The sphere is represented by x squared plus y squared plus z squared equals r squared, right? This has continuous first order partials. And let's say we're looking at some given z height. Let's look at the level curve at z equals, let's just say some value a, right? So we'll pick a plane here at some height. Let's say this is the height, z equals a. And we take the slice, and the level curve is this circle that's kind of parallel to the equator, but farther north, right? And so what we're looking at is the most rapid increase of the function. And the most rapid increase, if you take a tangent plane or a tangent line here, you get the gradient. It's where's the function increasing the fastest. And you'll notice that it's normal to the level curve at that moment. And maybe the best way to see it is think about the equator itself, right? If you look at the equator itself, then you can kind of see here, well, a tangent line is straight up and down, right? And so that means the gradient here is going to be normal to this level curve, which can be in either of these directions, right? And so this is the idea of the theorem. If you ever have to use level curves, well, you know that your gradient is normal to the level curves. And so let's wrap up this video with an example. Let's find the direction for which the directional derivative of f of xy is going to be the function 3x squared minus 4xy plus 2y squared at the point -2, 3 is a maximum. Also, what is the maximum value? Okay. And so here we're given a function, and we want to find the direction in which the directional derivative is increasing at a maximum. And what is the max value at this point, right? Well, we know which direction the directional derivative increases the most, and it's the gradient. The direction is the gradient. And we can calculate the gradient relatively quickly. It's the partial derivative with respect to x and the x component, the partial derivative with respect to y and the y component, which gives us 6x minus 4y, and then it looks like it's going to be minus 4y, excuse me, I have that backwards, minus 4x plus 4y. Okay. And then we can plug in, we're at the point 2, 3, right? And so since we're at the point 2, 3, we need the gradient at the point -2, 3, right? Yeah, -2, 3, excuse me. And so if we plug in -2, 3, well, it looks like we're going to get -12 minus 12, so -24. And then we're going to get negative times negative, so 8 plus 12, which is 20. And so here is a direction for which we're increasing the most. But usually when we describe directions, this u in the directional derivative is a unit vector, right? So we need a unit vector in the direction of the gradient of f at the point negative 2, 3, which is u, it's the gradient of f at the point negative 2, 3, divided by its magnitude. Because if you'll recall, that's how we find a unit vector in the direction of another vector, is you take that vector and then you scale it by 1 over its magnitude. And so this is going to be negative 24, 20 over square root of negative 24 squared plus 20 squared. And I'll just kind of skip some simplification here. And what you end up getting is, I mean, you can use a calculator and then distribute, and what you'll get is negative 6 root 61 over 61, comma 5 root 61 over 61. And this is the direction for which our function is increasing the most rapidly at the point negative 2, 3. And what is the maximum value? Well, the maximum value, right? So we found the direction. Check. The next one is, what is the maximum value? Well, the maximum value is the magnitude of the gradient, which is this piece down here. And so we can calculate this, right? It's equal to root, well, negative 24 squared plus 20 squared is if you use a calculator or multiply it out, you'll get root 976, and this can be simplified to 4 root 61. Okay, and so this is the max value, and it's changing in the direction given by negative 6 root 61 over 61, and then 5 root 61 over 61. And so this is an idea for applying the gradient and partial derivatives to finding in what direction is the maximum change, and then also what is the value of that change, right? Basically, what is the directional derivative evaluated there? So this concludes everything I would like to discuss about directional derivatives and the gradient. And where we'll go from here is finding maxima and minima of surfaces, right? So in single variable calculus, we learned how to find critical points and then use that to find local maxima, local minima, or global maxima, global minima, stuff like that. All these notions extend to multivariable calculus. And so we'll be discussing that next.